Tonight's program is called Radon as an Environmental Tracer for Geological Studies and is brought to you by the LSPA's Western Massachusetts Committee. I turn it over now to Guy Dalton, co-chair of this committee.
Thanks a lot, Michelle, and thanks everybody for joining us in this month's members meeting. My name is Guy Dalton with GZA in Springfield, and along with Phil Warner, I have the pleasure of co-chairing the Western Mass LSPA Committee. And I also have the privilege of introducing today's speakers, both with Durridge Company. I'll start with Carlos Bielicki. Carlos is the CEO at Durridge and a developer of scientific grade instruments for detecting radon and Thoron in air, soil, and water. Carlos is responsible for developing Durridge's strategic vision and leading the company's operations. He has a diverse background in high-tech executive management, ranging from venture-funded startups to established companies including Broadcom, AMD, IBM, and Nuance. He holds a BS and a Master's of Engineering degree in electrical engineering from Cornell. Dr. Stephen Sadler is the chief scientist at Durridge. After completing his PhD in 2014 in the high energy physics group at the University of Sheffield in the UK, Stephen joined Durridge as managing director of Durridge UK Limited. In 2018, Stephen became chief scientist at Durridge, at which time the role of Durridge UK expanded to include research and development of new products, including an ongoing collaboration with the University of Sheffield. Stephen has presented talks and posters at international conferences and is active in the field of radon measurement. With that, I will turn it over to Carlos for the presentation.
So thank you, Guy, once again for that. I also want to thank the LSPA for inviting us to speak today. It's an honor and a privilege, and it wouldn't have happened without the help of Geotech, who made the initial connection between Durridge and LSPA. So a big thank you to them as well. And perhaps most of all, thank you to all the attendees here today. I know that everybody's busy, and we have a lot of things that are pulling at our time. So the fact that you made time to come here today is very appreciated. Thank you for that. And with that, I'll lead us into this presentation. A couple of things. What Durridge does as a company, very briefly, we're located in Bielicki, Mass, and we develop scientific instruments and software mainly around radon capture and analytics. So our instruments do the measuring, and the software we develop does the analytics and the graphing of the data. In terms of what we're going to talk about today, well, we're the developer of the instrument, but we are familiar a bit with what our customers are doing with it. And so it's a bit of a survey of use cases of what our customers are doing in terms of utilizing radon as an environmental tracer. It's some pretty interesting stuff. And perhaps by the end of this, you might think about incorporating radon into your toolbox for remediation studies and assessments and that kind of thing. So, so with that, why don't we get right to it? And we'll start with, well, what is radon? It is a chemical element, more formally known as radon-222. It's a noble radioactive gas, and it is produced by the decay of uranium-238. Uranium has been around since the Earth was formed billions of years ago. So because uranium is ubiquitous around the planet, radon is too. Now, the thing about radon is it does have a bit of a sketchy reputation. Most of us think about radon, and most people outside this seminar think about radon in terms of what you see here on the left side, that it's harmful. It is true that if you're in a building, a home or a work site where the radon level is high, it can be harmful. If you breathe it over long periods of times, it's been proven to develop lung cancer in people who are exposed to it for prolonged periods. So there is a dark side to radon. However, there's also a good side to it, a helpful side to it, and that's as an environmental tracer. And that's what I'm here to talk about today. And let's start with why radon is a good environmental tracer. That might be the first question in many of your minds. Well, there's quite a list here. It's everywhere. So as I mentioned earlier, uranium's everywhere, and and radon is a product of uranium. So it's in the air, it's in the soil, it's in the rock, groundwater, all over the place. And that's what makes it suitable to large scale and long-term studies, because it covers such a wide area, and because it's been around and it's going to be around for a long time, radon's well suited for really any size of study that that's required. Another nice benefit of radon is it doesn't perturb the system that's being studied because it's part of the system that's being studied. And also related to that is there's no risk of environmental contamination. You're not injecting radon into soil or spraying it into the air or anything like that. It's already part of the environment, and so it's not contaminating it. In addition to these sort of natural features of radon, it is also very precisely detectable, and that's what our instrument does. Our instrument at Durridge is called the RAD7, and this device is designed to detect both radon and an isotope called Thoron. And lastly, and maybe I should have put this at the very top of the list, radon's free, and that makes it very attractive to people. It's very low cost. And you'll see as we go through the presentation here, not only is it a cost-effective tracer, but it's also time-effective. It tends to be pretty quick. So what are we going to talk about today with that background? A couple of use cases. So first, there are people who use our RAD7 and radon to measure radon in groundwater and surface water interactions. And so I'll talk to you about a project where there are pollutants leaching into the groundwater, which is then being fed into rivers and streams, and radon and Thoron were used to study that effect. I'll also have an example here of salt water and fresh water mixing that we'll talk about. Aside from groundwater and surface water interaction, vapor intrusion, which is probably something many people on this call are familiar with, I'll talk through how radon plays a role in vapor intrusion studies, and then talk about an example about PCE underneath a manufacturing facility and how radon was used for a study there. And then finally, I'll turn it over to Steve, our chief scientist, who will talk about NAPL, non-aqueous phase liquid survey, that was done at a site that experienced significant diesel fuel contamination. And again, how radon was used in that example. So, so without any further delay, let's go ahead and launch into this. Groundwater, surface water interactions. So how does radon play a role here, and why is it useful? Well, the key here to know is that groundwater carries higher radon than what's called surface waters, or rivers, streams, lake, coastal waters. And that's for a pretty simple, straightforward reason. Groundwater, since it runs underwater, it's running through soil, it's running over rocks, and it's absorbing radon as it goes. So it's going to have a higher radon concentration than, comparatively speaking, than those other types of waters. And so therefore, when you're studying these water bodies, the way that you can tell that there's groundwater is that you'll see peaks in the radon concentrations. There's various applications for this. Investigation of soil or groundwater contamination is one of them, and that's an example I'm about to talk about. Groundwater, surface water interactions, how are they interacting and why? And just an investigation of groundwater migration. How is groundwater moving? And this last one is a particularly important one that I'm seeing a lot of activity in developing countries, especially ones with drier climates that are depending on groundwater for drinking water. They really want to understand how is that groundwater moving. So, so that's kind of the summary of how radon is useful in these water types of interactions. Let's talk about a specific project. And so this first one is, it was actually a collaboration between Florida State and Chulalongkorn University in Thailand. And you see the picture there, you see the researchers on the vessel and those tubs in front of them holding the instrumentation. And so the project here, the purpose of it was to explore for groundwater pathways of pollution into the waterways of Thailand. It was, becoming a significant problem there. And so you see here the quote from one of the researchers that since radon is very concentrated in groundwater, it serves as a good tracer of where groundwater is discharging in. And I don't know how many of you are familiar with Thailand, but the Chao Phraya River is a pretty famous one there that runs through Bangkok. And they wanted to know, well, how much of this groundwater that's carrying pollutants in is actually discharging into the Chao Phraya River and the klongs, or the canals that kind of are offshoots of that river. So that was the point of the project here. The method that was used, and you can see there in the picture on the right, that's what was inside one of those bins from the previous slide. Those are 3 Rad-7s that are being employed to measure radon and thoron in the water. And so the method that was used here is first to measure radon, which has a half-life of 3.8 days. And because that amount of time is shorter than the flushing time of the canals, by measuring the radon, they were able to measure just how much radon was coming into those sections of the river that they were studying. So that was sort of part one. What's the volume of groundwater that's coming in? The second bullet here, you can see, is that they also were looking at thoron, and you might wonder, well, why? And actually, thoron turns out to be a pretty good prospecting tool because it has an extremely short half-life. Its half-life is only 56 seconds. And so the key here with thoron is that if you're detecting it, it means that you're close to where the groundwater is discharging into the river. You're close to that discharge point. And that's why they were interested in measuring both radon and thoron. It gave them a complete picture of what was going on in terms of the groundwater coming in. And so as a result of this project, this research team was able to show a very high correlation between the radon that was being measured and pollutants in the form of nitrogen and phosphate. And that they were able to determine that these pollutants were coming in from farms that were not too far away from these rivers and canals. And that the fertilizers were leaching into the groundwater, and then through the groundwater were being carried into the rivers. So it was a successful project. The graph that you see here on the right is actually pretty interesting. So let me explain it a little bit because it looks a bit complicated, but it's not really once you understand it. So you can see that the top axis says distance, and it goes 0, 5, 10, 15 kilometers. And on the bottom, you can see times, 10, 12, 14 o'clock. And this is all measures of thoron. So what they did was they were in the boat with the instruments, and they went down the river, and they measured the thoron that they were seeing. And you could see the peaks that are marked 1, 2, 3, and 4. That's where the thoron was peaking, and therefore they were able to determine that at those locations, and roughly speaking, it looks like about 8 kilometers from where they started, just over 10, around 13, and around 14. That's specifically where the groundwater was discharging into the river and carrying these pollutants in. So that's great because that's a useful data for them to consider for their remediation efforts, right? So anyway, that was the long and the short of this project. Again, using radon and thoron to determine how groundwater was moving pollutants into waterways. Now you see in the top right here, the lead researcher in this project is somebody named Professor Bill Burnett from Florida State. I give you his contact information there because if this type of thing is interesting to you and you'd like to learn more about it, you can feel free to contact Bill. He's a close friend of our company, and he'd be happy to answer any questions and be an advisor if you would like to learn more about these methods that were used. He's been doing this for decades, so he knows it cold. Okay, let's move on to another example, this with the US Geological Survey. And this is actually an ongoing project. Here, the USGS is examining the interactions of fresh and saline water under the sea floor in Monterey Bay, California. That's their study. And what they're trying to determine is they know that fresh water is mixing with seawater under the seafloor, but they want to understand how much of that mixing is fresh water that's coming from groundwater and how much of it might be surface runoff, like from rain. For their project, this is an important thing to determine. So you can see here in the picture the two lead researchers, Cordell and Ferdinand, and they've actually developed these buoys, these red buoys that carry RAD7s in them. And at this point, floating out there in Monterey Bay right now as we speak, I believe there's something like 8 to 10 of these out there measuring radon. And there's another, there's another picture of the buoy. And so what they're doing is they're using RAD7s, they're pulling up water, and so you might wonder, well, how is it that this instrument that I should have mentioned earlier perhaps measures radon in air? How is it measuring radon in water? And the way it's doing that is that we supply an accessory that aerates the water. It's called the Rad Aqua. And by aerating the water, the RAD7 instrument then can measure the radon, and we've developed some algorithms that would then tell the researchers how much radon is in that water. So the USGS is conducting this project right now, like I said, as we speak, and the final results aren't in, but the feedback that I've heard so far is that they are having success determining that a good fraction of the fresh water that's mixing under the seafloor there is in fact from groundwater. Again, in the upper right, if you'd like to learn more about this directly from the researcher, you have his contact information there. Feel free to contact him if this is of interest to you. And that leads us to polling question number 1. And the question is, what is it about Thoron that makes it useful for targeting groundwater discharge points? Is it that Thoron is easier to measure than radon? Thoron has a short half-life of 56 seconds. Thoron combines with pollutants, or Thoron is more common than radon. We'll give you about a minute to send in your answers. So please go ahead. Okay, we have most of the results in, and I'm not surprised. It's a very smart group we have here. The correct answer is the second answer, that Thoron has a short half-life of 56 seconds. Let me talk about the other answers though, just to, because it might be educational. Thoron is easier to measure than radon. It's actually more challenging to measure Thoron than it is to measure radon, and that is because of its short half-life. 56 seconds doesn't give you a whole lot of time to make sure you're measuring the Thoron that's in the sample that you're taking. So you have to make sure that the tubing that you're using is as short as possible, and make all kinds of, making sure that the pump is running at the right rate to push the Thoron through in the instrument. So for those reasons, because of that short half-life, Thoron is actually tougher to measure than radon. The third answer here, Thoron combines with pollutants. That's not actually true. It doesn't, and in any case, instruments like the RAD7 can accurately measure the Thoron concentration, so that's not really a factor. And Thoron is more common than radon. Well, in terms of in terms of being produced by elements in the earth, the amount of Thoron and radon that is being produced is actually about the same. However, because Thoron has a shorter half-life, there's much less Thoron available in the environment. So radon is actually more common than Thoron. So thank you for answering. More than 80% of the folks got that right who submitted answers. So thank you. I appreciate that. And now we'll move on to the next topic here. and that is radon for vapor intrusion studies. And so the question we're trying to answer here is how much VOC, volatile organic compound, how much VOC in a building is from an indoor or outdoor source around the building versus coming up through the subslab. And to determine this, it's very useful, and I'll talk through a case in a moment, but this is actually a pretty widespread use of radon as a tracer, maybe the most of the three that we're talking about here today. But you can calculate something called the attenuation factor that indicates how much of the radon beneath the subslab of a building is actually making it through and getting into the building. And the reason radon is useful for this is because there aren't any significant above ground radon sources. So whatever is coming through the slab, whatever ratio of radon gas is making it up through the slab, that's going to be the same ratio of anything else that's under the slab that's making it through. And so the way that you calculate the attenuation factor, if you look at the box in the lower left, is simply the alpha stands for attenuation factor. And so it's the concentration of indoor radon minus the concentration of outdoor radon. What's outdoor radon? That's radon that's in the background, right? As I said earlier, there's radon everywhere. So to know what's in the building, you really want to subtract that background radon from really the measurement that you're getting indoors. And then you want to divide that by the concentration of radon that's in the soil vapor. That'll give you the percentage of radon that's coming up through the subslab and into the building. So for example, if 10% of the soil vapor is entering the building and you're measuring in the building that actually more than a higher number than 10% of some VOC, then you pretty much know that whatever amount is over that 10%, there's a source either in the building or right outside the building that's contributing to the measurement that you actually took in the building. And that's how attenuation factors are useful. Now, something else to know about vapor intrusion studies and radon is that it is important to measure radon and VOCs continuously over time, just because there's a big variation. And if you take the approach of just taking an average over, a couple of weeks, you're really not going to see the true behavior of what's going on in that building. And so I borrowed this from an EPA presentation. There's a link there if you wanted to look at this a bit more closely. It's a presentation that's been delivered at past conference by the EPA, and I know they've worked in collaboration with Geosyntec and Jacobs and some other parties on this. But the graph on the bottom that you see there basically tells you what I'm talking about here. So in a particular building, radon and TCE were measured over a period of about 1.5 years. And the purple graph is radon, the green is TCE. And you can see, as you might expect, that in the colder months, there toward sort of the right of the middle of the graph, you see November, December, January, February, March. That's where the peaks are happening of the VOCs in this building. And that makes sense, right? Because when it's cold, the windows are closed, the doors are closed, the gases stay trapped inside the building. And that's typically when you're going to see the peak amounts. And if you're studying a building, particularly to recommend or install a mitigation system, you want to make sure that the system that you are developing and installing is going to take care of the peak amounts, because then the building will be safe throughout the year. And so that's why it's important to study the vapor concentrations for a long period, certainly longer than a few weeks, and preferably something like this 1 year to 1.5 years. So that's a little bit of context in terms of using radon for vapor intrusion. Now let's talk about an actual project. And the one I'm presenting to you here is from a company called Gannett Fleming. They are an environmental engineering company that perhaps several of you have heard of. They're headquartered in Pennsylvania with offices in Massachusetts, Connecticut, New Hampshire, basically throughout the US, and they also have some international locations as well. And so in this particular project, there was a large manufacturing facility in Wisconsin that had a source of PCE underneath it. And even though the samples of the indoor air that were taken were below any kind of level of concern, there was still a problem flagged by the Wisconsin Department of Natural Resources because they measured the concentration of PCE in below the slab, below the foundation of the building, and they found that the concentration was very high according to their standards, and there was too much of a risk of PCE, a higher than safe amount of PCE going into the building from below the subslab. And so at that point, after the WDNR study, they and the owners of the building were very close to approving and installing a vapor mitigation system to take care of this problem that had a price in over $100,000, right? A significant investment. So at that point, they called in Gannett Fleming to just verify these measurements. And so the method that Gannett Fleming used was essentially pretty straightforward. They took samples of indoor air and subslab air at 7 different locations around the facility. And they looked at the radon and the PCE, and very importantly, as I just mentioned, they did it during the heating and the non-heating seasons, right? So they took the proper length of time to really understand how the vapor emanation into the building was really working. And so as we just talked about, they took the radon concentrations under the slab and in the indoor air and calculated the actual attenuation factor that they were seeing at this facility. And so what was the result? Well, it turns out that Gannett Fleming's measurements were 1 or more orders of magnitude lower than the WDNR's default attenuation factor of 0.01. What does that mean? That means that Gannett Fleming determined that less of that PCE was actually coming up through the subslab than the WDNR had assumed. Now, it's important to understand here, the WDNR didn't actually calculate an attenuation factor. They just used their default of 0.01. And so by coming in and actually measuring the attenuation factor and determining that less PCE was entering the building than had been originally assumed, this company saved over $100,000 in a potentially unnecessary mitigation system cost. Again, the power of using radon as a tracer here. If you are interested in learning more about this project or using radon for vapor intrusion studies, there's a lot of literature out there on this, but in particular, Tony Miller, who's the environmental engineer for Gannett Fleming and who carried out this project and has carried out several projects like this and presented about them at several conferences, he'd be more than happy to hear from you and answer any questions you might have about this. Okay, so that takes us to polling question number 2. And you've heard me say this a few times over the last few slides. What is the attenuation factor formula? And so there's a few options here. The first is it the subslab radon divided by the indoor radon? Or is it the indoor radon times the subslab radon? Is it the outdoor radon concentration minus the indoor radon divided by the subslab radon? Or is it the indoor radon minus the outdoor radon divided by the subslab radon? You'll have a minute to provide your answers, please. Okay, again, smart group, no surprises here. So let me go through the answer. So the correct answer was the 4th one, indoor radon minus outdoor radon divided by subslab radon. So essentially that's giving you the percentage again of the radon from the subslab that's making it up through the foundation and into the building. So why are the other 3 not the right answer? Well, Well, if you look at the first one, what we're really after here is indoor radon as a percentage of the subslab radon, and this is kind of backwards. So that's not really the right answer. The second answer it just doesn't make a whole lot of sense to multiply the indoor radon by the subslab radon, because it's not clear for vapor intrusion studies what that will give you that would be helpful. And then the third answer, which was a little bit tricky, it just reverses the numerator. Is that what's on top? I think that is. So here we just said outdoor radon minus indoor radon, but really what you care about, remember, the outdoor radon is the background. So you really want to take the amount of radon that you measure inside the building and subtract the background, and then divide that by the subslab. But it looks like most of you got that, so thank you very much. And we can move on to the next slide. And this next section is where I'm going to hand it off to my colleague Steve Sadler, and he'll talk you through radon for NAPL studies.
Okay, thanks very much, Carlos. Hope everybody can hear and see me okay. Oh, could we, yeah, great, thanks. So as Carlos mentioned, I'm going to talk for a few minutes about the application of radon to NAPL studies. So NAPL stands for non-aqueous phase liquids. For example, petroleum products like gasoline, kerosene, diesel. So there are two different types of NAPL that we talk about. So the L NAPL, where the L stands for lighter than water, which is the things like the fuels that I mentioned, and D NAPL, where the D stands for denser than water. So this is things like chlorinated solvents, mineral oils, etc. You find these contaminants at sites like petrol stations, industrial sites, military sites, either in use or abandoned. I'm sure many of you are familiar with us. This is probably your bread and butter. So how does radon help with identifying, mapping and measuring these NAPL spills? Well, the key thing is that radon preferentially partitions out of soil gas and water into NAPL. So you can see that in this sketch on the right-hand side of the slide here. So if you're measuring radon either in the Vado zone, which is shown by the kind of grey box, or in the saturated zone, which is the kind of tan area at the bottom of the picture, you'll see like a background radon level outside of the area of the spill. But then when you get close to the source zone, the radon starts to drop off. And that's because some percentage of that radon that was in either the soil gas or the groundwater in the saturated zone is being taken up by the NAPL and is therefore not available for measurement. There are two different techniques where you can use radon to look for NAPL. So in the Vado zone, you'd, as I mentioned, you'd measure radon in soil gas, so the sort of air phase. And we're going to go through an example of that in the next few slides. And the second technique is to look for radon, to look for NAPL contamination in groundwater in the saturated zone, used by measuring radon in groundwater samples. Yeah, as I've already mentioned, it can be used to map contamination, which is going to be the main thrust of the example that we go through in these slides. But also to quantify contamination if you're able to make some assumptions or some measurements of other parameters of the soil on the site. And finally, to monitor remediation effectiveness if you're using a technique, for example, in situ air sparging or something like that, to try to remediate the NAPL contamination. Okay, next slide, please. So the project we're going to look at is one in Germany, an abandoned airfield. So this was work done back around 2002 by a guy called Michael Schubert in Germany and collaborators. So at this site, it was already known that there was a NAPL spill, and which had actually been investigated with traditional soil core sampling methods, where you take a soil core and send it off to a lab for analysis. And so this had revealed that there was a lot of contamination with diesel fuel in the Vado zone. So the aim here was to confirm those results using a radon survey. So next slide, please. So the equipment used was a continuous radon monitor, similar to our RAD7 instrument, and a soil gas probe. So with the RAD7, the measurement protocol for a project like this would be a series of 30-minute measurements, where for each one you would insert the soil probe into the soil and connect up the RAD7's inlet to the probe. First 5 minutes of the 30-minute run is sort of pumping the sample out of the soil and into the instrument's measurement chamber. That's followed by 5 minutes of waiting time for radioactive equilibrium to be reached. And following that, there's 20 minutes of counting time. The nice thing about this is that after the first 5 minutes of pumping, the sample is in the chamber. And so during the counting phase, the operator can actually pull up the soil probe and walk to the next site. And then have everything sort of set up and ready to go for the following measurement. And that's nice, especially if you've got as many as 209 samples to take, as was done in this case. So the samples here were all taken from a depth of 70 centimeters. So this was determined to be low enough to get below the level where sort of meteorological effects like changes in air pressure and temperature, things like that, can affect the measurement, because you want the only thing affecting the radon levels that you're measuring in the soil gas to be the sort of target, which is the NAPL contamination. You don't want confounding factors like these meteorological effects to confuse things. So in this case, the geology was known well enough that they could just assume homogeneous permeability and background radon distribution. So this was sandy soil. These are the conditions where this technique works best. So where you can assume this homogeneity. So it becomes a little bit tricky if you have differences in the amount of radon being emanated from the mineral matrix in different areas of the site. And similarly, if the permeability is different areas in the site, then you may have differences in the radon levels that are not depending on the NAPL contamination, which you're interested in. Finally, in clay or very wet soil, you have the problem that the radon diffusion length becomes so short that you risk missing sort of NAPL deposits with the soil probe, because they tend to be quite blobby in nature, and you can just get unlucky with the area that you choose to probe. Okay, next slide, please. Okay, so here are the results. So the red dashed line in this picture delineates the known extent of the NAPL contamination based on the soil coring measurements that were done previously. The black dots are the 209 soil gas sampling points, and the heat map is this is the soil radon map as reconstructed from those 209 measurement points of radon. So as you can see, the areas of low radon, which is shown by the lighter color, map quite nicely onto the known extent of the spill. And in fact, they give a slightly more detailed picture of what's going on. And there's a couple of areas there where the radon shows that there's contamination, which was missed by the soil coring. The benefits of the radon technique over the traditional technique are that you get your data instantly without the need to send off the samples to a lab for analysis. It also means that you can have a denser sampling grid, so less chance of missing blobs of NAPL contamination. Excuse me. So one limitation of this technique is that since the partition coefficients for different types of NAPL are broadly similar, it can't really tell you what is in the soil. It can give you a good idea of where it is, but you still need a few core samples to give you an idea of exactly what the contamination is. However, this is balanced out by the fact that it's less costly and time-consuming. The only equipment that you need is the continuous radon monitor and the soil gas probe. Okay, next slide, please. Okay, and this brings us on to polling question 3. So, true or false, radon surveys are effective for NAPL delineation and remediation because NAPL emits radon, which makes it easy to find. Is that true or false? Okay, looks like the results are in. So the answer is false. That's right. So NAPL doesn't emit radon. It actually absorbs it. So the signature of NAPL contamination is a radon deficit rather than a radon excess. Okay, so we just got a couple of slides about with a little bit more detail about our RAD7 technology before Carlos gives us a summary. So the RAD7 is a continuous radon and Thoron monitor, so it's slightly different from the kind of time integrating charcoal test kits or electret type devices that people might be familiar with if they've had a radon survey in their home or know someone that has. So they yield this, the RAD7 yields time series data, and it's an active instrument, which means it can actively pump a sample into the chamber. So for example, it's useful for these soil gas measurements. It works by electrostatic precipitation followed by alpha spectrometry. So that's a bit of a mouthful, but the electrostatic precipitation part just means that inside the measurement chamber, you have an electric field that points inwards towards an alpha particle detector. So the sample of air that's drawn into the instrument goes first through a filter, which filters out any existing airborne progeny, leaving the only radioactive species as radon and Thoron. Then when those decay in the chamber, this electric field collects charged daughter particles onto the surface of a detector, where their decays are then measured by the detector, which gives the spectrum that you can see in the top right of this picture. So the first thing to note is that each of those peaks corresponds to a different characteristic energy corresponding to a different species. So the A and the C peaks correspond to polonium-218 and 214, which are the daughter and granddaughter of radon. So these are the radon peaks. And then the B and the D peaks correspond to polonium-216 and polonium-212, which are the Thoron daughter and granddaughter peaks. The peak on the left that's not labeled is the long-lived polonium-210 contamination peak, which is it's a problem in other radon detectors using different technologies. But with our technology, you can just completely separate it out based on energy. Just throw away all the counts in those low energy bins. So the really nice thing about having this great peak separation is that you can firstly make independent and simultaneous measurements of radon and Thoron. And secondly, that you are not susceptible to this long-lived background. So this is the data that the RAD7 collects, but and you can print that out on a sort of cycle-by-cycle basis if you really want to dig into the detail of what's going on. But it also reports radon and Thoron concentrations in Picocuri's per litre units, which are most common over there in the States, or becquerels per meter cubed, which people seem to prefer in Europe and elsewhere. It's simple to use. It's just 4 buttons to control it with a simple user interface, and it interfaces with our sort of powerful capture software for Windows and Mac, which allows you to visualize and analyze data. Oh, I should say that the instrument has two different modes of operation as well. So we have sniff mode and normal mode. So sniff mode is for fastest response and uses just the polonium-218 peak in the A window there, whereas normal mode has a slightly longer response time and uses the A and the C peaks to get the maximum number of counts and the highest sensitivity. Okay, I think that's all I wanted to say about that. So final slide from me. So this is just a small selection of the accessories that we offer with the RAD7. So the RAD Aqua, you've already seen in action in Thailand. So this is our continuous radon in water accessory for the RAD7. Similarly, the RAD H2O is also a water accessory. So what these two instruments have in common is that their purpose is to bring a closed loop of air, including the RAD7 and its measurement chamber, into equilibrium with a water sample. The difference is that with the RAD Aqua, your water sample is continuously flowing, whereas with the RAD H2O, you take discrete samples in the bottle that you can see in the picture there, and hook it up to the RAD7 and make a measurement that way. The RAD H2O can be used either in the field or samples can be collected and taken back to a lab or a different facility for analysis. If you do that, it's just important to remember to take a note of the time and date of the sample collection, because from the moment that the radon sample is taken away from its supporting radium in the, well, wherever it was collected, it starts to decay. So it's important to know the time so that you can correct for that decay later. And finally, in the bottom right corner, you can see the soil gas probe alongside a RAD7. So this is the equipment that you would use for a survey like the one that we saw in Germany at the abandoned airfield. And with that, I'll hand it back to Carlos for the summary.
Okay, thank you, Steve. I appreciate that. So, this brings us to the last slide here, and I hope this has been educational for everyone. Hopefully most of you, or maybe even all of you, learned something new here, and that is that radon is and can be an accurate and cost-effective tracer for environmental remediation studies, and that it's been used in groundwater surface water interaction, vapor intrusion, and NAPL contamination cases. I encourage you to think about radon as a potential tool to add to your tool case for your work, because it is time effective and cost effective option. And if you'd like to consider this and learn more about it, feel free to contact us. We've got information on our website. We can point you to some documentation. And we can also put you in contact, perhaps most importantly, we can put you in contact with some folks who have been doing this for some time and can answer questions. With that brings us to the Q&A section of the presentation.
Great, Carlos and Stephen, thank you so much. Very interesting, generated a lot of questions. It's actually good to finish a little early because that gives us some time to answer more of the questions. Right now we have 12. Just so everybody knows, to fulfill your LSP credit requirement, we have to stay on till 5 o'clock. So at that time, I'll let you know. But if we need to go a little bit longer, maybe 5 minutes or so to finish up answering questions, we'll do that. So I'll start with the first question. And so this is for Carlos. Do the groundwater concentrations of radon vary whether it is passing through an unconsolidated versus a bedrock aquifer? And would you expect higher concentrations in a granitic aquifer?
So I can answer part of that. Part of that I didn't understand, because it's like I said, we developed the instrument, but we're not out there doing the work. But yes, there are certainly variations, and even as the groundwater traverses, the area that it flows through, it's going to run through different areas of soil and rock that have different radon concentrations, and it'll absorb a certain amount there. So yes, you can think of that. That's an accurate way to think about it, that you can see that the groundwater radon concentration can vary. The important thing is that for groundwater, it's always going to be measurably higher than the surface waters, and that's where you get the differentiation.
Got it. I think what I'll do is I'll go back and forth with questions for both of you. So I'm not peppering you, Carlos, with a bunch of questions and then on to Steve.
Excellent.
The first question for Stephen is, have regulators raised any concerns with measuring radon as part of a vapor intrusion assessment for VOC contamination? It seems to me that one could measure radon to assess vapor intrusion while avoiding generating VOC analytical, which might trigger additional regulatory requirements, such as an imminent hazard condition. So I guess the main question is, have regulators raised any concerns with measuring radon?
Not that I'm aware of, but Carlos, do you know any more about the US?
Yeah, so actually the EPA, and there might be some people from the EPA on this, I'm not sure, but I've certainly talked with folks from the EPA in the past, and they have they've made recommendations, or they have some term for it. So while I don't think that the method of using radon is regulated for vapor intrusion studies, there's certainly recommendations, and there's people at the EPA, as I mentioned before, working with environmental engineering companies who have a lot of enthusiasm about this technique and been studying it for many years. So I would say there's support for it from a regulatory point of view, at least from the EPA.
Excellent. Okay, the next question, I think this is for you, Carlos, is it sounds as though using continuous time series radon measurement in indoor air above the foundation slab might be a good way to identify when maximum vapor intrusion is occurring.
Absolutely true, yes. And that's perhaps what that the graph on that slide was showing, that if you do have an instrument in the building that you just leave running, and then these instruments are, whether it's from Durridge or some other company, these instruments are generally built for long-term measurements, and with the graphing capabilities that they come with, that's where you can see where the peaks are, and therefore sort of define your mitigation system around that. So yes, that's accurate.
Okay. Stephen, what kind of vertical profile would radon tracing provide for soils? Would you need to perform assessment at multiple depths to get a full picture?
Yes, and your spatial resolution will, I guess, depend on the soil type. So as I mentioned, in clay or waterlogged soil, the radon diffusion length is a lot shorter. So in that case, you can get you'd be able to get a sort of better vertical spatial resolution. Whereas if you're in a soil that's quite sandy and dry, the radon is able to diffuse further through the soil. So that sort of reduce your spatial resolution of your depth profile.
Sure. Carlos, this question is for you. In determining an attenuation factor, is it necessary to collect an outdoor ambient air sample to determine radon concentration, or is there standard radon background concentrations that are used?
No, radon even outdoors can vary. So the recommendation is, wherever that building is where your project is taking place, that you do go outside that building locally and measure the what we call the background, the outdoor, the background radon, and use what you measure there locally to subtract from the indoor to determine the attenuation factor.
So I think you've answered the second part of this question, which I didn't read. But it sounds like because radon concentrations do vary over time, you always want to get an outdoor background air concentration. You don't want to use a value from a previous sampling event. Is that correct?
Yes, that's correct.
Okay. Excellent. Thank you. All right. So the next question for Steve, is the count time for sniff mode shorter?
Actually, for a given radon concentration and a given statistical uncertainty, it's longer. So in sniff mode, you're only sensitive to the polonium-218 decays. So the sensitivity is lower. So the number of counts that you get per unit radon concentration is roughly half what you get in normal mode, because normal mode includes both the polonium-218 and the subsequent polonium-214 decays. And roughly speaking, there's one polonium-214 decay for every polonium-218 decay.
Let's see. Okay, Carlos, question for you. Is the aerator also used for groundwater analysis?
Yeah, and we have customers that that use both. You remember the aerator for the continuous source measurement was called Rad Aqua, and the other one for testing water samples was called Rad H2O. So we have customers that do both. We have customers that look at groundwater. They dig bore wells into the ground, and they pump the water up from the well and through the Rad Aqua, so that they're doing an in situ measurement, which is what the Rad Aqua is good for. And then we also have customers who take groundwater samples and bring them back to the lab, or not even always bring them back to the lab. They might have a Rad H2O there right on site, but they take the groundwater samples and then they use that accessory connected to the Rad 7. So both are used. It's really a matter of, I think, the requirements of the project and the preference of the researchers and the engineers.
Great. All right, so this question really cuts to the chase, and it came up when Stephen was speaking, but either one of you can answer it. It's, are the instruments available for rental, and is there a budgetary number for purchase of the Rad 7 unit?
Hey, Chief Scientist, would you like to answer that one? No, okay, I'll take that one. Yes, they are available for rental. I mentioned at the beginning of the webinar Geotech. And Geotech is our sort of lead distributor in North America, and they do have Rad 7. Yeah, they have a rental fleet of Rad 7. So they are available from Geotech. I would encourage you to contact them. And the list price for the Rad 7 is $7,300.
All right, excellent. So the next question is, how much are these radon? Oh, we just answered that one. How long does it take to sample at one location? And say 10 soil gas samples will be collected. Does that mean 10 Rad 7s are needed?
We'll pass that one to Steve.
Sorry, Guy, could you repeat the question? I think you just cut out on my end for a moment.
Oh, sure. How long does it take to sample at one location? And say 10 soil gas samples will be collected. Does that mean 10 Rad 7s are needed?
If you want to collect them simultaneously, you would need 10, but each measurement only takes 30 minutes in total. So if you wanted to make those measurements sort of one after the other, then you could do that, but it would take 5 hours total.
Okay, this next question is a little bit similar to an earlier question we had about the impacts of granite on the samples. And the question is, when you measure indoor radon, do you have to take into account radon generated by granite counters or sinks in kitchens and bathrooms?
Yeah, I can take that one if you like, Carlos.
Sure.
In general, no. So the indoor radon levels generally, the effects of things like granite countertops is pretty insignificant as a driver of indoor radon levels in general. I think part of that has to do with the fact that they tend to be polished, so the surface area is very low. There's not much fine surface structure there, so there's not a very large surface for the radon to escape from. But yeah, it just tends to be dominated by other sources, really.
Okay. Next question. I think this is for Carlos. Couldn't you have a discrepancy between radon and VOCs if VOCs are coming through an atypical preferential pathway, such as a sewer line?
Yeah, I think that's possible. So that's something to guard against. I mean, at the same time, radon could be coming up through there too. But I think in taking measurements of, you want to make sure that you're, if you're calculating attenuation factor, you want to make sure that that the VOCs and the radon that you're measuring the samples are taken in a place so that you can be assured that, that it's coming up through the slab. So that would be my, 2 cents on that one.
Okay. The next question, in calculating the attenuation factor, is there variability in the subslab radon measurements, or are concentrations relatively constant throughout a small building footprint, such as a single family dwelling?
Generally speaking, it's going to be pretty similar, but you can still have variations. And that's why, for instance, in the Gannett Fleming example that we talked about, they took samples. Admittedly, that was a large manufacturing facility, but they did pick 7 different locations to do this. In a home, maybe instead of 7, there's 2 or 3, but it's always a good idea to use a couple of different locations just so you can see what that variability might be.
Yeah, I think you would typically take the subslab and indoor measurements as close in time as possible together, just in case there's any sort of meteorological effects that are changing with time. Could mess up your results.
Yeah, that's very true. And one of those effects that Steve is referring to could be just a barometric pressure. If you have a storm system coming in, pressure goes low, you can suddenly start seeing higher concentrations. So it is important to make sure you take those measurements one after another.
Okay, I think I know the answer to this one, and I think the answer is the RAD7, but maybe there is another answer. What method is used for air sampling for radon, and what is the analysis?
That's a Steve question for sure.
Yeah, well, the RAD7. I mean, any continuous radon monitor would do it, but I'm always going to plug our instrument. So
I think maybe what they're getting at is, we do like a TO15 analysis for VOCs. Is there, if you're submitting a laboratory sample, is there a lab method for radon analysis in there?
So there are standard methods for radon, for sort of indoor radon measurements, which Carlos, you may know better than me about the specific, the protocol specific to the United States. I can't really say too much more than that on my end, sorry.
I think
there's the 48-hour test that most people know from real estate, but for vapor intrusion studies, I'd have to get back to you with an answer to that. I'm not aware of any regulations on that.
Okay, looks like we just have 2 more questions actually. This one is, are you aware of any radon mitigation ramifications for using radon as a tracer? I believe 4 picocuries per liter is a recommended level for radon mitigation in residences. Detecting concentrations above this level in a residential building could potentially result in additional costs associated with addressing this newly discovered radon intrusion.
That's absolutely correct, and you could consider that a side benefit of using radon as a tracer for vapor intrusion, because you're really doing 2 things, right? You're determining how much of the vapor is coming up through the slab, but if at the same time you're getting a measurement, if it's a building where people either live or work, and you're getting higher than 4 picocuries, yes, you've also discovered there's a radon problem that should be mitigated. So you kind of get a 2-for-1 benefit there for sure.
Okay. Geez, you guys are doing a great job answering these questions. We have 1 left. We're going to finish up right around 5 o'clock. So the last question is, at what point in time does a radon half-life start ticking? After it leaves a bedrock fracture, after it partitions from the dissolved phase to a gas phase, and how is a RAD7 response adjusted to account for half-life relative to sample location?
Yeah, I'll take that one, sure. So the answer is that it's the moment when it stops being in contact with its supporting parent nuclide, so which is radium-226 in the mineral matrix. If you're collecting it from from groundwater. So yeah, that's the point at which the clock starts ticking, and that's the time that you want to note down on any RAD H2O measurement, so that you can correct the results. If you measure it at a later time, you can correct for for decay, just using the well-known radioactive decay equation and the radon half-life.